Okay, good day, viewers and students. Okay, today we will continue discussing curvilinear motion, cylindrical components. In the past two lessons, we have discussed about curvilinear motions in terms of rectangular components and normal and tangential components. Okay, when we say rectangular components, there are two types. Okay, we can do it in two-dimensional form or in three-dimensional form, while the other one we can approach, okay, you can solve the curvilinear motion by dividing it into tangential and normal components. Okay, so today we will have a different approach. Okay, so we discuss about cylindrical components. Okay, so to begin with, let us consider this figure. Okay, so I will draw a horizontal line. So let us say at the middle of this horizontal line we have a point O, and then we have this. Okay, and then okay, so let us say that we have a line. Okay, this is R, and then we have an angle theta relative to the horizontal. Okay, so when we say cylindrical components, okay, okay, so we can have it in 2D. Okay, okay, so when we say 2D, we can also call it as polar components. There is also a 3D in this one, so but we will discuss it later. Okay, polar components. When we say polar components, it is composed of, okay, two components also, radial component and we have angular component. Okay, so these are the two types. Okay, so when we say 2D or polar components, we have radial component and angular component. Okay, so how does it works? Okay, so please consider. Okay, so in cylindrical components, it is, okay, it is applicable. Okay, it is applicable. Okay, so if, okay, if your your motion is rotating. Okay, okay, so it is applicable in rotating motion, but somehow we need, okay, so this is his application. Okay, rotating motion, so we need, okay, to consider uh, that there are two, okay, there are two components that is changing. Okay, so we have the angle. Okay, so how does it works? Actually, in a polar component, it is moving this way. Okay, your theta. Okay, so your theta is changing. Okay, or your angle. Okay, is moving. Okay, clockwise, counterclockwise, or clockwise. Okay, so here our example here is it is moving, what is commonly used, it is moving counterclockwise. Okay, so as your theta increases, okay, so it is rotating counterclockwise, your R might be also increases. Okay, so let us say this will be your R prime, and let us say this is, okay, so this is your theta, and then it will become theta prime. Okay, so from that, there is a possibility that there is a change in your radius. Okay, so from this side of radius, as your angle or theta increases, okay, uh, let us say consider it as counterclockwise. If it is rotating in counterclockwise motion, so it also increases or decreases. So depending on the situation, it increase or decrease, meaning there is a change. Okay, so therefore there are two unit, okay, two components that we are referring to. So we have the UR. Okay, so since this is the radius, so parallel to that, this is your UR. Okay, so and then we have what we call as U theta. Okay, so in this case, okay, so if it is already in this part, so you also have, this will be your UR and this will be your U theta. Okay, so notice that it is changing. Okay, so if it already went in this direction, okay, so your theta will be measured again, okay, from this horizontal line, okay, from the right side. So your UR here will be this. Okay, so let us say this is your theta 2. Okay, so your UR here will be like here, and then your U theta will be here. Okay, so as soon as he rotates, there is a possibility that there is a change in your R or radial component and your theta or your angular component. So your radial component is your R, and your angular component is theta. Okay, so the most common is that it moves. Okay, so in this diagram, okay, in polar components, it is drawn, okay, from, okay, from 0 to 360 degrees, okay, or 0 to 2 pi radians, into which, okay, this is 2 pi in the 2 pi region, into which it rotates, okay, counterclockwise. So this is how you graph your polar components. Okay, so what will, okay, so if you have a given theta, okay, a value of theta, what will be your R component, which means your radius, okay, your R or your radius or your radial component is the dependent variable, while your theta is your independent variable. So you can say that your R is a function of your theta. Okay, you can represent, okay, let us make this more beautiful to look at. Okay, so it should be straight. Okay, so that is how you draw. Okay, so if this is your theta, your UR should be in this manner. Okay, so please take note that your UR and your U theta should be also 90 degrees with each other or perpendicular. Okay, so your R is a function of your theta. Okay, so there is a possibility that, okay, you can do it this way. Okay, so either it is you represent it that your radius is a function of your theta or your angular component. So you can also denote that your r might be a function of time. Let us say f1t, and your theta is also a function of time. Let us say f2t. Okay? So it can be represented either this way or this way. Okay? Okay. So maybe, okay, so we'll go into maybe we'll go in introducing to you the formulas that you need to know. Okay, so maybe, okay, so I will get another board here. Okay, so these are the formulas that you need to memorize. Okay, so since we have a radial and tangential component, okay, so your velocity, okay, your velocity radial, okay, so let us say formulas, this is for velocity. So your velocity has two components. So your VR, or your radial velocity, is equivalent to dr over dt. Okay, so we can also represent that as r with a single dot at the top. It means first derivative of r with respect to time. And then we have v theta. Okay, so your v theta can be represented, okay, so your v theta, or your angular velocity, is can be represented as r theta, r multiplied by times d theta over dt, or can be represented by r multiplied by theta with a single dot at the top. Okay, so d theta over t is also equivalent to this, which means it is the derivative of your theta, or your angle, with respect to time. Okay, and also your total velocity, or your resultant velocity for that, will be equivalent to vr squared plus v theta squared. Okay, so that is for your velocity. Okay, so for your acceleration, these are the formulas that you need to memorize. Okay, for acceleration, it will be like this. So your acceleration region in radial component, okay, is equivalent to d squared r over dt squared minus r times d theta over dt. Okay, so this is the formula. Okay, so you can also represent this as r with a double dot at the top minus r times theta. Okay, okay, so there will be a squared here. Okay, sorry, d squared r over dt squared minus r times d theta over dt quantity squared. Okay, so this is theta with a single dot to the power of 2, which means, okay, so these two are equivalent. Okay, so we also have, okay, a theta, or acceleration, okay? This is radial acceleration, so this is angular acceleration. So your angular acceleration will be equivalent to r, okay, multiplied by d squared theta, okay, over dt squared plus 2 dr over dt multiplied by d theta over dt. Okay, so this is also equivalent to r with theta with double dot at the top plus 2r with single dot at the top and theta with single dot at the top. Okay, so when these dots respectively, it means, okay, so if it is single dot, it means that it is differentiated once with respect to time. If this is, if you see 2 dot at the top, which means it is derived twice with respect to time. Okay, so that's why d squared r over dt squared is equivalent to r with double dot at the top, and d theta over dt is theta with single dot at the top. Okay, one dot represents, okay, so I will repeat, one dot represents, okay, first derivative with respect to time, and then double dot means, okay, second derivative with respect to time. Okay, so that is how it is. And also, okay, so your a, okay, I will just put it here since we have no space, is equivalent to also to ar squared plus at squared. Okay, so that is how we compute your ar and your at. Okay, and then to add, okay, so maybe, okay, so in this is in scalar form, so in vector form it will be like this. For velocity, okay, let us say vector form, okay, so your velocity, your v is equivalent, okay, directional v r theta r plus vt v theta, okay, v r u r plus v theta u theta. Okay, and then your acceleration, okay, so this is in a vector components. Okay, u r and u theta when squared, okay, when you square root the sum of their squares, okay, the sum of their squares of u r and u theta should be equal to 1, okay, and then your acceleration will be ar ur plus v u theta, okay, no, a theta minus u theta. Okay, again, the sum of squares of your ur and u theta respectively should be equal to 1. Okay, so therefore from this we can get that the sum of squares of your VR and your V theta is equal to V. And then the sum of squares of your radial acceleration A or AR and A theta is A. Okay? So please take note that your R represents radial component and your theta represents angular component. Okay? So these are the formulas for two-dimensional cylindrical components. Okay? So in the next video, we will be discuss what if it has three components. Okay? So what if it has a z component, okay, or a distance component? Okay, so we will be discussing that on the next video.